Good morning, everybody. Happy Monday. Hope everybody is doing well. So say hello if you're in the chat, and of course, ask questions. And so I apologize. I opened up week 4 a little late. So I opened that up. I apologize for that. And then it came up since somebody was asking about the other lecture videos that I realized I forgot to talk about. Periodic trends. So I'll be watching the chat for any issues. And I think everything's going well. People are turning in assignments. Lab reports look pretty great. They do take me a while to grade, but everything seems to be going pretty nicely. So let's start off with periodic trends since I neglected that topic. And so let's go over a few of them. So we'll start off with the basic one of just metallic character. And we can see that as we go from left to right, that it gets less metallic. So we can put more metallic this way, our arrow. And so let's look at other trends. So let's look at our atomic radius. Switch colors for this one. And so radius is pretty interesting. So we'll come up with our overall trend. And so first of all, it increases as we go down. That's pretty self-explanatory. And so that makes sense. We're increasing shells as we go down, right? So as we go down each row, so a new onion ring. But what happens when we move across the periodic table? Because it's actually not so intuitive. And so for that, we'll look back at our Lewis dot structure. So let's look at nitrogen versus fluorine. And so they're both filling up the 2p as we go across. And let's just fill in our 2s. So then we'll fill in nitrogen. So 1, 2, and then 1, 2, 3. So 5 valence electrons versus fluorine, which has 7. So 1, 2, 3, 4, 5, 6, 7. And so we find that fluorine actually has a smaller radius. And so that's because they're filling in electrons at the same energy level. So by comparison, fluorine has more electrons. Therefore, right, it's more negative charge at that same distance. So from the nucleus, it's able to then hold in the radius tighter. And so we say in general, our radius decreases then as we go across, as we fill in. And actually, let me pull up a graph because there are a few anomalies. Give me a second here. I'm looking for a chart. Let's see, I'm not finding the graph I'm looking for. All right, we'll come back to it because there can be a few exceptions. Okay, I think I finally found what I was looking for because we have this little graph where we can compare our atomic radius. Although this one looks pretty normal, just decreasing as we go across. All right, so let's look at other trends. We'll come back to this later. And so other trends that we want to look at are going to be electron affinity. And so electron affinity generally increases as we go across and also up. And so our element with our greatest electron affinity is fluorine. And so it's on a scale of 4. And so it's the most electronegative. And so actually let's talk about, I kind of screwed that up. All right. So we have two concepts actually that we need to distinguish. So we have electron affinity. Versus electronegativity. So they both kind of run in this general trend. Negativity, negativity. And so let's define them. So electron affinity and electron negativity are pretty similar, but the little difference is electronegativity is in a bond. So that's basically measuring how much an atom is pulling electron density towards it in a bond. And electron affinity is actually a gaseous reaction, and it would be of that just compound, or of that atom, I mean. And so in general, it would be metal plus electron gives us metal anion. And so then thinking about like fluorine plus an electron gives you fluoride. And then is that energetically favorable or not? And so both of those generally run in this increasing as we go left to right and then up. So electronegativity. The only discrepancy is that fluorine has the greatest electronegativity. This is where I misspoke a little earlier. Electronegativity. And chlorine actually has technically the highest electron affinity. And that's probably due to chlorine's slightly larger radius, so that's probably more favorable with balancing that negative charge. All right, so that should help with our atomic radius and periodic trends. So now let's go and start our chapter. And so last time we looked at ionic bonds, so those were transfer of electrons. And now we're looking at covalent bonds. And so these are from electrons that are actually shared by atoms. And so we'll look at this. So electrons then that are shared by atoms are called our bonding pairs. And so we might also have lone pairs on atoms that are not shared but just belong to that atom, and also known as non-bonding pairs. And so let's take a closer look at water. And before we even look at this, so let's think back. So we were talking about our Lewis dot structures last time. And so let's just warm up. So what's our Lewis dot structure of oxygen and hydrogen? So just take a moment. All right, so we should have gotten something. So oxygen, group 6, these two lone pairs of electrons. And then we have our single electron. So this gives us a hint, kind of prime for bonding. And then each hydrogen, and we could even go ahead and draw 2 to prepare to make water. And this also tells us how many, what I like to say, how many electrons we're bringing to the party, our total number of valence electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8 total to play with and kind of share among these 3. And so that's how we got the structure here. And this is something that you want to start playing with and practicing with. And so I can kind of see, again, this is where those terms come into play. So I can see those lone pairs on our oxygen right away. All right, so they're not involved in bonding. But then we had those 2 lone pairs. And then our hydrogen each have 1 electron. And so that's a good indication that those might come together. to form a bond. So each one is bringing one electron to that bond. So that makes a normal bond. And I'm going to rewrite this because I want to show these two electrons then is just a little line. So a single line to indicate a single bond. So each line is 2 electrons. And so now let's look at the diatomics and kind of why they're diatomic. So this kind of helps us predict the type of bond, at least in a simple sense. So we could start with hydrogen again. So hydrogen, just like before, they each have 1 electron. We can draw a little mechanism. So my half arrow shows that we just have 1 electron movement. And so then now we make our single bond with hydrogen. So now let's try fluorine. So take a minute or less, try to draw fluorine. Start with the Lewis dot structure. And if you're in the chat, you can feel free to describe your structure. And so we should have started off with our Lewis dot structure looking something like this. And I might as well draw a second one next to it. So 7 valence electrons. So again, we have 3 lone pairs on each one, or as they call them, our non-bonding pairs. So they're already paired. So they're kind of happy, at least in the sense for now. So we'll find that these lone pairs could go on to react later, but that's not really relevant. But again, we have these 1 electrons and they're going to come together to make a bond. And so there's our fluorine. And so chlorine, of course, would be pretty similar. I'm just going to sketch that out quickly. So bromine and iodine would also look the same number of valence electrons. So now go ahead and try oxygen. See if you can draw that structure. Describe it in the chat. So how many bonds did you get? And you should have gotten 2. And you can always predict it from our Lewis dot structure. So I'll go ahead and redraw it now. I'll kind of orient it as well so it's ready to go. And so we kind of have these 2 Lewis dot structures sitting next to each other. Well, they both have 2 lone pairs. And then each of them has 2 lone electrons. And so what if we make 2 bonds then? And so that gives us this structure. And so again, this is a decent representation. And so what we're also trying to do, I should have probably explained, is we're trying to make sure that everybody's satisfied by the octet rule. And so this has 1, 2, 3, 4, 5, 6, 7, 8 electrons that it feels. Same thing with this one. 1, 2, 3, 4, 5, 6, 7, 8. Notice the hydrogen only needs 2, so it's satisfied by the duet rule since it's only filling that 1s orbital. And so fluorine, same thing, 1, 2, 3, 4, 5, 6, 7, 8. Go ahead and try nitrogen for a second. So start with the Lewis dot structure and try to predict how many bonds. And so if we got our Lewis dot structure, so 2 dots somewhere, 3 lone dots on the side. So if we draw kind of 2 of those nitrogens, again, we have 10 total valence electrons from our 2 nitrogens. So how can we put those together? And so we should have gotten something that looks like that with a triple bond between those 2 nitrogens. And so how do we predict the type of bond? And so there's a couple of different things. So we can go back to our ionic bond and we'll think about the naming. And remember, those were all group 1, group 2, and all these metals. And then there was a few aluminum, gallium, indium, right, tin. So some of these still form compounds, but these are all metals. Don't forget, right, we have our staircase. But we also have this thing called electronegativity. So that was part of our periodic trend that we were discussing. And now we can look at some numbers. So I had rounded fluorine's electronegativity to 4. Here it's given as 3.98. So you could see that discrepancy. So it's depending on the chart. And so what we see is bonding is kind of this continuum. And again, this is why it depends like on the exact bonding scenario that you're looking at. You'd want to analyze, a variety of different things. So how it reacts, maybe get the electronics information, try to understand the bonding and the bond length. So all of that is important. But this is a general guideline. And so looking back at the ionic, again, net metal plus a non-metal, where the electrons were transferred. So usually you have a large difference in electronegativity. And so let's look at sodium chloride as an example. And so chloride, let me pull up my calculator. So 3.16. Oh, minus our sodium, so 0.93, and a fairly large difference of 2.23, again, relatively speaking. And so anything greater than 2 is considered an ionic bond. And so below that, so from zero point 0.4 roughly to 2 is considered a polar covalent. And so polar covalent means electrons are shared unequally, but again, it's not so much that the electrons are actually transferred. And so one polar molecule would be like hydrochloric acid. So let's compare. And so we have chlorine again, so I'll go ahead and punch in 3.16. Let's look up hydrogens. 2.1. So 1.06 as the difference. So that falls in between there. So that helps to tell us that's a polar covalent bond. And then smaller than that, so from 0 to 0.4 is a covalent bond. And again, it's just the difference between them. And so let's just take the example of chlorine. Again, relatively electronegative, but obviously 3.16 minus itself is going to give us 0. So all the diatomics are going to be completely nonpolar. So does that kind of help? And again, if you have questions, even if it's about lab or something else unrelated, I can certainly address the question and then go back to our lecture. All right. And so we were kind of seeing this with our diatomics, but let's go over it. And so we saw when two atoms shared one pair of electrons, we just call that a single covalent bond. Again, a single bond is just two electrons. Saw that with water as well. And then, like you saw with our oxygen diatomic, those shared two pairs of electrons in our double bond. So we would write it like so. And so we can have other elements that double bond with each other or themselves. So carbon and oxygen do a lot of bonding. And this could be just any generic organic formate and acetone are pretty similar to this. We have a bunch of sulfurs, and phosphorus can also bond. Nitrogen and do double bonds with itself or other elements. So just keep that in mind. And then like we saw with nitrogen, we can also have a triple covalent bond. And you can also have carbon, nitrogen, oxygen, phosphorus, triple bond, sulfur. All those can triple bond. And so sometimes you see carbon and oxygen. So in CO, that would be a triple bond. So that's one kind of common example. There's also cyanide. So that's another kind of common one. All right, so now let's just kind of look at, in general, what kind of structures they make, what geometry these look like. And we'll try to focus just on, the main geometries. And so if we're looking at group 4, so right, that's group 4 with carbon, silicon, germanium. And so all of them tend to make these kind of tetrahedral complexes. So methane is our classic example. And so I drew it in 3D. And you don't have to draw it like this, but it's good to kind of practice because you want to show its geometry. And so its geometry is tetrahedral. And this is where molecule kits might also be useful. So that could help. And so again, tetrahedral, how I drew it, these are both in the plane of the board with the fat wedge here that's showing that it's coming out of the plane of the board, and the dashes show behind. And let's just draw another compound. So silicon tetrachloride is another example. Oh, what am I doing? I'm just filling in the electrons. So there's our structure, octet rule satisfied. And so now let's look at group 5. So group 5 can make two different kind of geometries. Any guesses to a substance you might know? So the one I was thinking of is ammonia. This is one type of compound. And so we start with our Lewis dot structure for nitrogen. So again, we had that lone pair. And so it has this tendency to do this 3 coordinate. Again, I'm trying to show our 3D structure. And so we can refer back to our tetrahedral. So let me see. And so I'm trying to show. So right, we have our tetrahedral basis. But now instead of having, right, a lone pair on top, or a substituent, excuse me, we have a lone pair on top. So still tetrahedral basis, but now, and again, note how it's not flat, right? Trying to move that so you can see, sorry. Got to work on this webcam, but you can see how it's not flat. And so what that is telling us is its geometry is trigonal pyramidal, kind of like a pyramid, right? And again, this is really prime for action. So this tells us a little bit about the reactivity. We won't get into it too much today, but ammonia is a base. You might know it as a household cleaner, but these electrons are important. And so phosphorus can do that as well. So phosphorus trichloride, but these can be nasty compounds. They're pretty reactive. So especially like phosphines. So they want to react with oxygen because of those double bonds. And so because of that, we can make these sorts of compounds. So this would be phosphorus trichloride oxide. And again, this is just kind of the structure it tends to make. So this would be tetrahedral if it did this. Or these group 5 compounds. And so this is usually now with our lower rows. So starting in our 3rd row. And they can also do these kind of extended octet or expanded octet. And so phosphorus can do PCl5. And so it would look like this. See, I'm trying to remember if you need to know this geometry for this class specifically. I have to look at your notes. But the geometry is called trigonal bipyramidal. And so you can kind of tell why we have our triangle in the middle. And then we have kind of our 2 pyramids on each halves. I was trying to see if I have a molecule kit handy with that geometry. And striking out though. Oh, I don't know what happened to my molecule. So this would be SE3D hybridization, but that's not quite too relevant for this class. We don't need to know orbitals. So just appreciate that shape though, and know that these group 5 can also do expanded octet. And then the other thing I want to point out And a lot of books say this. Your textbook might even say this. But usually it says, oh, it's only the third row and above because now they can invoke d orbitals. And that's actually not true. Well, in the sense that they don't need d orbitals to interact. So they're actually still interacting with the p orbitals. And so you don't need to invoke d. Why the second row does not form those compounds is simply they're too small. And so theoretically, NF5 does kind of exist. The problem is that you need to have really elongated NF fluorine bonds on the Z axis here to make it work. So this might exist, I think, in the gas phase, but they've done some modeling with it. But that's kind of the issue. It has nothing to do with d orbitals. And so now let's look at group 6. So can anyone name our kind of classic group 6 example? Any guesses? So our classic group 6 is water. Of course, H2O. And that also means we have all the analogous compounds. So sulfur, hydrogen disulfide, and selenium disulfide. Let me just write that the other way. So H2S. So all these look the same. And again, notice they have 2 lone pairs. And so they can also do expanded octet. Oh, let's do geometry. So geometry would be bent. Again, we're starting with our tetrahedral framework. So, right, starting again, tetrahedral, except 2 of these have lone pairs. The other 2 are substituents. And so, like I said, sulfur can also do expanded octets. Oh, sorry, I got excited about expanded octets. So we can have sulfur hexafluoride. And so this compound, often you see people on the internet like breathing this in. So this is a gas, and it's a heavy gas. And so what it does is it makes your voice deep. So right, you probably are aware that helium makes your voice light. So it does that since it's a lighter gas, so it's less dense. So that's why your voice gets high. And so by contrast, sulfur hexafluoride has the opposite effect. So it makes your voice deep. I definitely do not encourage you to do that. You could definitely accidentally asphyxiate yourself and breathe in too much gas. You shouldn't really be playing with gas, not even helium. Definitely don't do it without a partner or someone to watch you. But yeah, definitely don't play with gases. And this geometry is octahedral. So now let's look at group 7. And so group 7, a lot of the times they just do the single bond. So we saw that with itself or with HF. And we can also find that they can do some interesting compounds. And so some examples would be like II3 or F3, some variation of this. ICL3. I've seen all of these. So take a second to try to draw this out. How might it go? And if you need more time, go back, pause the video, also redraw these structures. So the best thing for chemistry is to practice and practice again. And you can start off even, I'll do the II31. It doesn't matter which one you pick. So just start off with 3 bonds to everybody. And so now I'm just kind of thinking, well, iodine, right? They have 7 valence electrons. And I'm going to go ahead and fill in all of those. So those are in just a normal bond. And right, so if this iodine has 7 valence electrons, well, it has 3 involved in bonding. So that means it has 2 left over. And of course, we could double count our total number of electrons. So again, II3, each one has 7 valence electrons times 4. That means we have 28 total electrons in this system. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and then 25, 26, 27, 28. All right, that matches back up. And so this one, the geometry is T-shaped, but I won't write that down since we don't need to know it for this class. So, and let's at least note the expanded octet. So iodine does have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total electrons. So it does technically violate the octet rule. We're saying this iodine feels 10 electrons, but again, it's okay to have expanded octets from time to time. And so that's the other thing with the structures is you're trying to kind of get the octet rule satisfied. Obviously, sometimes we have exceptions. And then we also want to minimize formal charges, but I'll go over what that definition is. Right now, we haven't really had that be a problem. And so let's first look at our group 8 compounds. And so we said, right, well, group 8, those are our noble gases, and they are unreactive. Well, again, chemistry is all about getting things to react and forcing things. And so as they get larger, especially, this leads to them being more susceptible to forming compounds. And so we have xenon actually gives us 2 of our compounds. So we have xenon difluoride. And this is giving you a hint at covalent naming. So with ionic, right, we didn't have any prefixes, but now, since in our covalent bonding, we can have different ratios just based upon how it bonds differently. So we need this prefix to help us. And now we can say xenon tetrafluoride. And so let's draw out those 2 structures. And so again, xenon difluoride, I'm just going to start by drawing a bond to each of our fluorines, filling in our octet rule. Then it's basically, well, how many are left? Xenon had 8, so 2 involved in bonding, and then 1, 2, 3, 4, 5, 6. So that's 3 lone pairs on xenon. And this is a linear geometry. That's at least easy to see. So go ahead, see if you can try xenon tetrafluoride. Give everyone a minute or so. So how do your structures go? You could even start with this one. You can always start fresh. I'm just looking at what we drew. Like, well, we have this. Okay, so now let's just say these two electrons are involved in this bond. Well, that means we still have two lone pairs. So that is indeed the structure. And so if you can kind of tell what I drew, so the xenon and the four fluorines are in the plane of the paper, and then you have to think about the lone pairs going in and out of the plane of the board. And I could also redraw it from another perspective if this helps. So again, now showing the four fluorines and kind of that octahedral axis with the square planar geometry and those lone pairs going in what I call that up-down Z axis there. And so this geometry would be square planar. Any questions? Just letting people take that in for a second. Again, don't be shy in the chat. Well, let's go back to naming. And so again, different from ionic. So ionic, let's just go back and recap just so we're all on the same page. Where's our good ionic compounds? So right, we said we had our metal ending, we had "ide", we added our anion, right? And then we used for our type 2, we had our prefixes, or our prefixes, our Roman numerals. We had our Roman numerals that said our oxidation state. And so now let's shift gears. So again, this was ionic compounds. We're going to covalent. And so for covalent, I'm sorry, I'm allergic to everything apparently. So we're coming up with this conclusion that we can't just determine our formula from saying the two names, because with our covalent compounds, they can combine in a lot of different combinations. And so just taking nitrogen and oxygen, for example, they form in a 1-to-1 ratio, 1-to-2, a 2-to-1, 2-to-3, 2-to-4, 2-to-5. So how do you distinguish all that? And so we don't use oxidation states. So you can still use oxidation states to kind of describe covalent compounds, but at that point becomes more of a bookkeeping. And so instead, we just have to use our prefixes. And so usually we write the name of the element with the smallest group number first. And then you write your element with the greatest row number first. And then our prefixes indicate our number of atoms. And then if we only have one atom of the first element, it's usually omitted. So let's go back and name all these. So now we can name them. So NO, this would be nitrogen. So we name our first one, and then monoxide to say that there's one. NO2 is nitrogen. Again, we don't need a prefix for the first one. And now dioxide. N2O. Now we can put our dinitrogen oxide. And again, do your best with spelling. And if you get anything wrong on a quiz that you think, you need credit for, I know it happens, you swap the vowels or have too many, I will definitely be lenient. Just do your best to try to spell so I can, tell what you're going for. So N2O3. Now this would be dinitrogen trioxide, or 3 oxygens. So N2O4, now we're at dinitrogen tetraoxide. And let's just finish up this last one. So N2O5, dinitrogen pentaoxide. So questions, so you can kind of see that. So covalent naming, I feel, is a little easier than ionic. So ionic, right, you're trying to determine those oxidation states as for those transition metals. But this one, you just state how many. So with covalent, right, we just use our prefixes to indicate how many. That's a lot easier. So try these 3 examples. So take a few seconds. So feel free to post your answers. So A, we should get nitrogen triiodide. And B, so this would be phosphorus pentachloride. And then C, be tetraphosphorus decasulfide. So any questions about those? So hopefully that, again, feels easier than our ionic compounds. And so something else that we want to be able to do is determine how to get our formula mass or our molecular mass. And so again, this is made convenient by our periodic table. And so let's go over what we're saying here. Let me scroll down so that's all clear. And we're looking at all this. And so our molecular mass is the mass of an individual molecule or formula unit. And so that's known as our molecular mass or molecular weight. And we can also use that to determine the mass of 1 mole. And so what this is saying is, well, let's say we want to know, right, the mass of one molecule of water. So from the periodic table. And so they rounded so we can look at ours. So we have a little bit more precise values. So 1.008 for hydrogen. So again, your numbers could vary slightly, but roughly, right, we take our number, multiply it by 2, because there's 2 of them in our formula. Again, draw it out if you need it more explicitly stated. And so now we're just adding up all the components. So 2 AMUs for our 2 hydrogens. So each one at 1. So 2 times 1.01 plus our 16 atomic mass units for oxygen. Again, we have like 15.99 on our periodic table, or your number could vary slightly. And so we add those, and then we get our mass of one molecule. So 18.02 atomic mass units. But this number isn't that relevant for us, really. And so again, that's where our mole comes into play. And we said that we scaled it such that one molecule is then, we can translate that to mean the same amount in grams. So this AMU is basically grams. And so we could say 1 mole of water then has a mass of 18 grams. So, and you often see so many abbreviations. It's kind of annoying, even in this course. I don't know why. So you see like AW or FW, MW, all that is the same thing. It is just saying what is the mass of the compound. And right, read the problem and then it makes sense. Do I need it in atomic mass units? Are we talking about one molecule? Or are we talking about a molar amount in grams? Let's go ahead and practice getting the mass of something. And what's a good compound? So let's do one. So let's do limonene. And the only reason I'm thinking about limonene is someone was asking me about how they might make a candy with limonene. And so I got limonene on the brain. So this is a terpene. And it gives the lemon spell in lemons. And so its formula is C10H16. And so what is the molecular weight of limonene? And so we can add it up. So let's go ahead and do it together. So our mass of carbon from our periodic table is 12.011. Then there were 10 of them from our formula. So times 10. Then plus 16 times our mass of hydrogen. So 1.008. Or again, you could round to 1.01 or even round to 1. And so do we get something like this for our molecular weight then? So we should get about 136.24 grams or so. And I'll just write in parentheses, right, or one molecule is 136.24 AMU. Questions about that one? Here we go. So this is the list that I was referring to. So these are the only geometries that you're really, we'll say, responsible for. And so let's look at some of these examples. And so go ahead, see if you can draw this out. So try BF3. If we draw this out, so maybe you want to start by totaling the total number of electrons that we have. So boron has 3 valence electrons. Fluorine is 7 times 3, so 21. So we have 24 electrons here. And so again, easiest thing, kind of just draw that. And we have 24 electrons, so 8 times 3 is 24 from how they're distributed. And so let's talk about a few things. And so let's go ahead and also define what a formal charge is. And so formal charge is, again, just more bookkeeping. And so what it is it's our number of electrons, number of valence electrons. So like from the periodic table. And then minus the number of bonds and minus the number of electrons. And you might see a few little variations on this formula, but I'll kind of explain it. And so let's go over this one and this structure. And well, let's point out why it's unusual. Any guesses? And so we have one problem. The problem is that boron is not satisfied by the octet rule. So it only has 6 total electrons. But if we look at everything else, so again, we only have 24 electrons to play with. So we can't change that. And then we want to satisfy the octet rule. And then the other thing I'd mentioned was formal charges. And so that's where this helps us, is that our formal charges are 0. So that helps us show that this is a good structure. And so let's look at this. And let's also compare why this is a better structure. And so if we look at this, so boron, let's calculate the formal charge here. So number of valence electrons, right, we said was 3. So 3 minus the number of bonds, so 1, 2, 3. And then we have no electrons, so 0. So our formal charge is 0. And we don't need to write that we have a formal charge of 0. Normally, I'm just doing it right now. But you definitely want to indicate if you do have a formal charge. And so if we repeat that for fluorine, so no formal charge. So 7 minus 1, 2, 3, 4, 5, 6 minus 1. So that gives us 0. So all of these have 0. So that looks good. And my other kind of thing with chemistry is I don't want people to get hung up on like, well, what's the right structure? Because you want to be able to analyze your structure and say why it's not a good structure. And what I mean by that is, well, let's take this alternative structure. So what if you had tried drawing something like this in an attempt to satisfy the octet rule for boron? And let's talk about why this isn't such a great structure. All right, we have something like this drawn. And so let's first count that we have the correct number of electrons, because I think that's the most important thing in your Lewis dot structure. So this would be like for an exam, is you want to make sure you have the correct number of total electrons. And so we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Perfect. We still have 24. And now looking at this, well, the octet rule is satisfied for everybody. So that looks good. But what about our formal charges? And so let's check that out. So boron, now it's going to be, I'm trying to show my work. So 3, again, for a number of valence electrons. Now minus number of bonds. So 1, 2, 3, 4. No electrons on there. But that leaves us with a -1 charge, formal charge. So I'm going to indicate this by writing my little negative sign there. I've circled that. And let's look at our formal charge on our fluorine. And so that's the other thing about your formal charges. Your formal charges need to add up to the overall charge of the molecule. Well, if we have a neutral molecule, then our formal charges have to cancel out. And so now if we look at this one, so fluorine 7 minus 1, 2, 3, 4. So that's -3 minus, let me write that out. So 7 minus 4 minus 2. So y'all can follow what I said. So that leaves us with a +1. And so this is what's bad about this structure. And so the other rule for our formal charges is that we usually want the more electronegative element to carry the negative charge, except in this case, our fluorine has the positive charge. So that's not good. So that's why this structure is less ideal. And this is a better structure. Does that make sense? And so on an exam, right, even if you end up drawing this, then you could say, not great, or, this is a better structure, some sort of indication that you're thinking of that. So let's look at another one. And so now is a good time to mention that aluminum trichloride is a weird one. So aluminum trichloride, you might expect this to be an ionic compound, and it does get named both ways. So this is a weird one. But its true behavior is covalent. So if you were to look up how it actually behaves, it's more covalent in nature. So this is another one with that trigonal planar geometry. And so both of these have no lone pairs, and so that means they lay flat. So this is an odd one. All right, now let's look at tetrahedral. And so do you remember our tetrahedral example that we had listed? So methane should come to mind. So those are kind of the classic ones. So see if you can draw ammonium. So ammonium is NH4 plus. So take a second to do that, or at least try. So let's start walking through it. So I just want to total up my number of electrons first. So nitrogen brings 5, hydrogen each brings 1, so times 4. And then with our plus charge, that means we're subtracting an electron. That means -1. So that means we have 8 electrons in our system. So then we should get something that looks, let me draw that a little better. Like so. So we have our 4 nitrogens in this tetrahedral geometry. So you can really see that now. And then don't forget our formal charge. And so I'm going to check our nitrogen. And so nitrogen, 5 valence electrons, minus 1, 2, 3, 4 bonds. So yes, indeed, nitrogen is carrying the formal charge. So that looks good for our structure. Looking for questions. And then, so moving back to trigonal pyramidal. So which one was that again? Do you remember? So classic example, remember, was ammonia. And anything else in the group 5. And then we had bent. And so we have our classic water, of course. H2O with our 2 lone pairs. And let's go ahead, try and draw the Lewis dot structure of SO2. So see what you get. So let's look at this one. So we have SO2. So both of those are group 6. So 6 times 3 is 18 electrons. And let's see. So how can we arrange them? And we could do something like this. So right, we said oxygen likes to make 2 bonds. But then let's see, we're at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We have 2 extra electrons. And so it's best to place them on our sulfur. So yes, we violated the octet rule. So sulfur feels 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But if we look at our formal charges, so formal charges 6 minus 1, 2, 3, 4, 5, 6 is 0. Sulfur is also 0. So this is actually our best structure. And then I also want to point out, so this is actually a different angle. So this is what I would call our kind of classic bent. And this has an angle of about 104.5 degrees. And then this one, it only has one lone pair and it's going to be a little bit wider at about 119 degrees or so, or 120-ish. And some people refer to this as V-shaped, but otherwise it's just referred to as bent as well. Right. Any questions about that? And so I want to stop there. So we'll continue tomorrow then, or not tomorrow, Wednesday with polar molecules and go over how you tell it's polar. And then we'll look some more at these organic structures. So I will stick around on stream in case there are any more questions. And then like you have been doing, submit questions. I can cover them during the stream as well, so you can get your answers or questions answered live. And yeah, just ask questions. Let me know if you need help. I've been getting emails from y'all and helping y'all there too. So that seems to be hopefully working for people. Again, let me know if you want more streaming time. Happy to accommodate. All right. Have an excellent Monday and a great start to your week. Again, email me early and often if you need help. I will talk to you later.